Beginning with this video, we're going to be looking at second-order differential equations. Before we get too far into that, I'd like to take just a minute and remind you what a second-order differential equation is. At the very beginning of the course, I briefly touched on the different ways in which differential equations can be classified. Differential equations can be linear or nonlinear. They can be first order, second order, third order, fourth order, or higher orders. They can be of first or second or third degree, and so on. And if you looked at the Unit 0 material for the course, then you may have gotten a slightly better introduction to that from section 1.3 in this textbook. But before we go on, I want to take just a minute and remind you what a first order differential equation is and what a second order differential equation is and how they're different, so that you'll know when you start looking at these, which aspect of the equation you're given is the thing that tells you that it's a second order equation. A first order differential equation might look something like this. I'm just making one up here for the purposes of illustration. What's important here is that the derivative we're given, this could also have been written as y prime. Oh, and I've mixed my variables again. Let's make that a t. This is a first order differential equation because I'm taking the first derivative. The right-hand side here of the equation is the first derivative of some function y. This is a second order differential equation. It's the same right-hand side, but the left-hand side, the piece that's telling us that this is a derivative, and that this is the derivative of some function y, is also telling us that it's the second derivative. Of course, I can also write this as y double prime. And if everything else is the same, it's simply this piece here that tells you whether it's a first order or a second order or a third order differential equation. So in this chapter, we're going to be looking at second order differential equations. Things that look like, I'll just copy this one out again, things that look like this. But of course, they could also look like this. Notice the difference here is that I've taken, actually, let me add just a little bit to it. Why not? I've got my y, which I had in the previous one. I have a term that has a y in it, but I also have a term that has a first derivative in it. So now I have a second derivative equation that is a second derivative, and it contains the first derivative. So in the same way that a first order differential equation can contain the solution as part of the expression of the derivative, the second order equation can contain the first derivative and the original equation, or the solution that we're looking for, as a part of the equation that we're given. So in this chapter, we're going to be working with this type of equation. I've just copied that last example down that I had because I wanted to make a point before continuing that this equation, as we've already discussed, can be written in this form. And in general, second order differential equations, maybe I should do this as a comparison. I'll do that. First order differential equations take the form, or can take the form, often take the form, of the derivative is equal to a function of t and y. And of course, y is also a function of t. Second order differential equations often take the form of functions of t and y and the derivative function dt, which I could write instead as t y of t y prime. And that's essentially what I've got going on here. I have a function. The left-hand side is the second derivative. the second derivative notation, right? It's this particular form in this case. It may sometimes be in this form. The right-hand side is a function that contains t's, y's, and first derivatives, y primes. T's, y's, there's my t, there's my y, and there's my y prime. In another example I gave you, lost my pointer. This is also a function of t, y, and y prime, but the coefficient of y prime is 0. So this is the form that second order differential equations frequently take. It's worth noticing that, let me get my pen, that a second order differential equation can be written as some function of t times y prime plus some other function of t times y plus some third function of t. Your textbook uses g here, so I will do the same. Doesn't really matter, it's just what they call it. And so I'll go back up to my previous example. My p of t in my previous example is 3t. My q of t is 10. And my g of t is 0. This is a term that has no y's and no y primes in it. It's analogous to the constant term in a polynomial. So if we have y equals 3x squared plus 2x minus 1 in a polynomial, we have a power of 2 here, a power of 1 here, and a power of 0, and therefore no x's here. So it is just an analogy, though, because this is a different situation. This is a function. This is also a function, but it's a function that's made up of other functions, one of which is itself a derivative, right? So this last term here might be a constant, but it might also be a function of just t. So if I wanted to demonstrate that, I could give you an example by adding to my previous example plus 6t. This could be 10ty, right? These are just examples. I'm changing these up just because they're helping to illustrate this form more than anything else. Normally when you're given a function, you'll be given a function, and you'll have to determine whether or not this last term here, which is a function of t, is present in the equation. Well, it is present in the equation. It's just that the coefficient is 0, so we don't see it. In the same way that there's an x right here, we just don't see it because its power is 0. So I'm going to erase this because I don't want it to stay on the screen. I don't want it to confuse things, but it's kind of an analogy to that. The other thing I'm going to do now is subtract this term, subtract this term, and I won't subtract that term from both sides, which gives me the same equation in a slightly different form. Actually, it's going to be minus p of t y prime minus q of t y equals g of t. And because p of t and g of t, or well, g of t as well, but p of t and q of t are some functions and we don't really know what they are until we know what they are, I can say this is actually plus, right? Because I'm just writing the form. I'm just explaining what the form of the thing looks like at this point. And this is what you have in your textbook. Notice a couple things here. P of t and q of t do not depend on y. Sure, there's a y here, there's a y prime here, but the function q of t itself and p of t itself do not depend on y. There's no y in those functions. Now, there can be, but in this case, there are not. And when a differential equation takes this form, when it looks like this, a second order differential equation, we say that it's linear. A linear second order differential equation has the form y double prime plus a function of t with no y in it times y prime plus a different function of t with no y in it, times y is equal to a third function of t with no y in it. It's not multiplied by y, it's not multiplied by a derivative of y. This form of a second order differential equation is a linear form. If you find that you have something that's close but not quite right, for example, if you have p of t times y double prime plus q of t times y prime plus r of t times y plus s of t equals 0, or I guess I'll be consistent and say that that is equals s of t, then in order to get it into this form, notice there's no coefficient function here for y double prime. All I need to do is divide each term, or divide both sides by p of t. And you'll notice here I've used capital letters instead of the lowercase letters I was using before. And then I just define q divided by p is little p. So now this function here, this rational function, equates to this p of t. And this rational function, right, I can define r over p to be little q. So now I have this function equating to this function, and so on. We are going to be restricting our study of second-order differential equations to linear second-order differential equations. There are such things as nonlinear second-order differential equations, but analysis of these is quite difficult and really beyond the scope of this class. So we're going to restrict ourselves to linear differential equations as we tackle the second order. The other assumption we're going to make is that the functions p, q, and g are continuous. And hopefully you'll remember from our work on the existence and uniqueness theorem that there's an important reason for continuity in the study of differential equations. From now on, or at least for this chapter, I can't remember what comes in chapter 4. I'll be really honest. I don't know if we discuss anything about discontinuous functions. I doubt it. But at least for chapter 3, I'm confident in saying that we will restrict our study of second order differential equations to those in which these three functions are continuous. So we can assume the continuity of these three functions as we study in this chapter. We don't need to prove it or demonstrate it or really even discuss it. If I give you a differential equation, or if you see one in the textbook or on an assignment, a quiz, or an exam, in this form, in this chapter, you could assume that the functions that fall into these positions, once this thing is in this form, you can assume that those functions are continuous. It will be interesting to investigate what an initial value problem looks like in this setting. We're used to seeing differential equations of the first order, such as, for example, y prime equals, well, I'll just use the same one, 3ty plus 10. And if I'm given an initial value problem, then that information includes initial values, initial conditions, right? In the case of a second order differential equation, that's not enough. If I want to solve this for a particular solution, then I'm just using my previous example. There's nothing magical about this equation. I just made it up. I don't even know what strategy I might use to solve it. I will need some initial conditions, but if you'll recall, essentially what we're doing when we solve a differential equation of the first order is we're trying to get it into a form so that I can integrate both sides and find out what y is. And then once I know what y is, I can plug 0 in for t, 1 in for y, and that will let me determine what my constant of integration was, right? In this case, I'm going to have to integrate twice. So I'm going to need to know, in order to figure out what my constant of integration is, I'm going to need to know initial conditions like this to get from the first derivative back to the original function. But to get from the second derivative back to the first derivative, I'm also going to need a second pair of initial conditions, a second set of initial values. So this is what an initial value problem would look like in the first order, which we're familiar with, and this is what one looks like in the second order. I need two sets of initial conditions, the ones that I'm used to getting, but also another set here. Okay, one more piece of vocabulary, and then we're actually ready to start working on some of these. If I take get my pencil here, if I take a second order differential equation, such as the one that I've been playing with, this is a generic one, y double prime plus p of t times y prime plus q of t times y equals g of t. That's a second order linear differential equation. And if I change that g of t, or it's not so much that I want to change it, but if the case arises, see, I'll use blue here, that g of t equals 0, that function is 0, then we call these, the equations in this particular form, we call these homogeneous. In the rest of this video, we're going to be working exclusively with homogeneous second-order differential equations. And in fact, we're going to be working with differential equations whose coefficient functions here are constants. So at least for this section, our differential equations are second order, so they're of this form, but g of t is 0, which makes them second order, they're linear, second order homogeneous differential equations. And this is the case where p of t and q of t are constant functions, right? So a and b are just constants here, and g is 0. That's what we're going to be working on in this section. I'm taking a step back with this first example because I want to use it sort of to drive home a point. This is a first order differential equation. And in fact, I want to start by changing the form that it's in and write it like this, make it a homogeneous equation. Well, it is a homogeneous equation. I just put it into a more standard form. And I want to talk about what is the possibility for a solution here. Now, we could do this the long way. We could say that this means that, given this equation, dy dx, I'm going to use t, dy dt equals y, divide both sides by y, multiply both sides by dt, integrate both sides, we get the natural log of y equals t plus a constant, so y equals e to the k, e to the t. We've done this problem many times before, but what's interesting here is that we probably could have come to this conclusion without doing any of this work here, because if you think about it for just a moment even, you would recognize that a function is equal to its derivative. That doesn't happen very often, but one of the places that it does happen is y equals e to the t. And in fact, once we have a solution to a differential equation, I'll write this like this. If y is a solution to a differential equation such as y prime equals f of t y, then ky is also a solution for any k that's a real number. So in this case, I have y equals k e to the t is the general solution to the differential equation y equals y prime, or y prime equals y. There we go. Now something else to observe here. Actually, I'm going to go back up here and and do it a slightly different way. Another solution to this differential equation is y equals negative e to the t, because the derivative of negative e to the t is negative the derivative of e to the t, which is e to the t. So you get the same thing again. So here, for both of these y's, both of them satisfy this equation, right? Both of them satisfy this differential equation. Well, another way to think about that is k equaling -1. So there are sort of two approaches here. One is that there are two solutions to this equation, and one is that there is only one general solution to the equation where k, because it's a real number, can be negative. There's something else we need to look at, and that is the possibility that y equals e to the rt, where r is some real number. Well, in the case of this first order differential equation, if I take the derivative of this with respect to t, I'm going to get y prime equals r e to the rt, and now y prime, which is r e to the rt, and y, which is e to the rt, are not equal unless r is 1. So there's only one case in which this is the solution to our original differential equation. And that case is where r is equal to 1. But there's another similar situation in which we might be able to use this other solution, this e to the rt. And that is if we introduce, say, a as a constant. Notice that in this equation up here, I have 1 times y prime minus 1 times y equals 0. Here I have 1 times y prime minus something potentially other than 1 times y equals 0. Now, a could turn out to be 1, but let's just say for the moment that we just don't know, right? We don't know what it is. If I now try to use e to the rt for y, let's just do it this way. Let's put our e to the rt in there. My y, I claim, is e to the rt, and my y prime is r e to the rt. Well, now I have an e to the rt in both of these terms. I can factor that out. I'm left with r minus a, and so either e to the rt equals 0 or r minus a equals 0. Well, e to the rt never equals 0 because e to any power will be positive, right? Remember that the graph of e to the something, e to the anything, either looks like this or it looks like this. It's never 0 or less than 0. So this factor cannot be 0. There's nothing we can do with that. But this factor here tells us that r equals a. So if I have a differential equation that looks like this, where instead of just a y prime minus y equals 0, I have a y prime minus some constant equals 0, then a solution is e to the rt. Where am I? A solution is y equals e to the rt, not just y equals e to the t. And the culminating fact, I think, here that's really quite interesting is that if this is a solution, if this is my equation, this is my solution, then this a right here equals the coefficient of r, right? Equals the coefficient of t. It equals the constant that we end up pulling down from the exponent because we're using the chain rule to differentiate e to the rt. And that's something to keep in mind as we look at the first example we're going to do of a second order differential equation. It will be very much like this, but that's the thing that's happening here. It's happening here. It'll happen in the second order when we get to that point. The thing that I find so fascinating about this is that a can in fact be 1. Right? A can be 1, which is what we had in this case up here. A can be 1, but if a is 1, so is r, right? Because they have to be equal. If a is something other than 1, then r is that same value. If we have a value other than 1 in this position here, then this a, for this to be a solution, this value here must be the same as that value there. I just think that's really quite interesting. Now watch what happens when I take this from this first order level, if you will, to a second order differential equation of the same form. Just to be clear, the form that I'm talking about is this form that we started with, the second derivative of y with respect to t is equal to some function of t, y, and dy dt. And of course, another way to write that is that the second derivative is equal to a function of t, y, and y prime. And this is what we have here. It's not quite in that form at this point, right? To put it in that form, I could just add the y prime and the 6y to both sides, and I would have a differential equation in this form. As it happens, I don't want it in that form for what I am going to do with it here in a minute. So I'm going to go ahead and erase that second line, but I think I've made the point that this is a differential equation, a second order differential equation in this form. Let's erase that. And then let's use the strategy that we did before, where we said, let's let y equal e to the rt and see if we assume that that's our y, that's our a solution, a general solution, then what happens if we find y prime and y double prime and plug all three of those in here? Do we in fact get 0? If we do, then this is a solution and we can go on from there. There's some interesting things that will happen as a result of this. So what I'm going to do now is take this equation. Well, actually, I'll go find y prime and y double prime first. Y prime is r e to the rt, and y double prime is r squared e to the rt. And now I'm going to take these and plug them into this. I have y double prime minus y prime minus 6 times y equals 0. Y double prime I found to be r squared e to the rt. Y prime is just r e to the rt, and y was e to the rt. Well, what's interesting here is that I now I have an e to the rt in every single one of these terms. So let's factor that out. I get e to the rt times r squared minus r minus 6 equals 0. Well, we know how to solve these, right? This is a polynomial, and this factor times this factor equals 0. So that means that either e to the rt equals 0 or r squared minus r minus 6 equals 0, or both, right? Except that this can't equal 0. Remember, this is an exponential function, and even if r is negative, the function e to the rt cannot be negative. So this has no solution, so we're just going to disregard it. But this has a solution. Let's see, I think I'll just factor. I think this factors. I'm going to get r, I think 2 and 3, and minus 3, but plus 2. So r equals negative 2 or 3 are two of my solutions. Well, those are two of my solutions. Those are two solutions to this equation here. But what I'm trying to solve is this equation here. And I'm proposing that this expression here, this equation here, is a solution to that. So if y equals rt is a solution, and r is either negative 2 or 3, then I have two solutions. Y equals e to the negative 2t, and y equals e to the 3t. And of course, I have any multiple of those will also work. So I'll put some k values in front. So I have now two solutions, two general solutions to this differential equation. Here's another interesting observation I'd like to make before we go on with that, with this problem. And that is this, that this differential equation right here looks awfully similar, at least in its structure, to this quadratic equation. Here I have the second derivative of y minus the first derivative of y minus, if you will, the 0th derivative of y times 6. Here I have the second power of r minus the first power of r minus the 0th power of r equals 0. So these are the same in structure. This has to do with derivatives and this has to do with exponents. But if I had, for example, y double prime minus 4y prime minus 45y equals 0. And I did this same thing here. I let y equal e to the rt. Then my y prime is going to be this, my y double prime is going to be that, and I'm going to be able to factor out that e to the rt, and it's e to the rt, and it's going to leave me with this r squared and this r and this, there's no r here at all. It's the same thing is going to happen. The only thing that's going to be different is the coefficients. So I can jump straight from this to this, e to the rt times r squared minus 4r minus 45 equals 0. And then I can factor that. That turns out to be 5 and 9. Let's see, I'll put the 9 there and the 5 there, and it's minus 4, so minus 9. So I have r equals negative 5 and 9. So in this case, I did the whole thing. I wrote out what the potential solution was, and I came to the conclusion that this differential equation, if something like this is a solution, is rewritable in this form here, and then I just factored this to find my r values. And then I used my r values to write my general solutions. I can skip all of this stuff here and just go straight from here to here. What I would recommend is that you write somewhere in here y equals e to the rt for the very reason that I highlighted down here. So when we got to this point right here in this first example, I said, well, those are my solutions. Except they weren't my solution. They weren't the solutions to the problem I was trying to solve. They were only the solutions to this quadratic equation, not the solutions to the original problem. So once I found my r values, I still had work to do. So for that reason, I think it's a really, really good idea to write in what the solution is that you're proposing, so that when you find your r values, you can plug them in here, rather than just saying, these are my answers. I'm doing this here because I'm trying to squeeze in a sub example. I'm going to erase this one in a minute because we're not quite done with this problem. My point in squeezing this in is that this second order differential equation can be, the solutions can be found, right? The general solution can be found simply by mimicking this structure here and writing out this quadratic, setting this quadratic equal to 0, and then remembering that the solutions to that go in here. Now, this is the point I was at making this video when I decided I really needed to back up and talk a little bit about the constant times a solution is also a solution, and the sum of two solutions is also a solution. And I wrote in that video, at the very end of that video, that a solution, the most general solution, is y equals the sum of the two scaled solutions. So I have negative 2t e to the negative 2t plus k2 e to the 3t. This is my general solution to this differential equation. Remember we said that k1 could be, k1 and k2 were any real number. So k1 could be 0, which means that a general solution is k2 e to the 3t. K2 could be 0, which means that a general solution is k1 e to the negative 2t. And of course, if k1 and k2 are anything other than 0, then you have the whole 9 yards, right? You have the potential for the sum of the two solutions, scaled solutions, to be a solution as well. So there are actually infinitely many solutions here, as is the case for any differential equation before you plug in initial conditions. We don't have any initial conditions here yet. I'm going to introduce some here in just a minute. But at this point, if all you're given is a differential equation and you're asked to solve it, the best that you can do is to come up with the general solution. If you don't have initial conditions, or if you don't have enough initial conditions, then this is as far as you can get. So for the problem that I was initially given, this is my solution. In the event, however, that you get some initial conditions, then there's more that we can do with this situation. I can take my general solution and I can say that I know that, let's just write this as k1 e to the negative 2, I'll leave that empty, plus k2 e to the 3, I'll leave that empty. That's my t value. And I'll use a different pencil here. I'm told that y of 0 is 3. That means that when t is 0, y is 3. And I can put those values in here when t is 0, y is 3. And then I can sort this out. That gives me 3, well, e to the 0 power, right? This is it. That's going to be 0. E to the 0 power is 1. So that gives me 3 equals k1 plus k2. So I have this. And then I also have a second set of initial conditions or initial values, but I can't plug those in here because this is the solution. This is y. I'm told y prime. So if this is true, then I need to figure out what y prime is so that I can plug these values into it. You can do this at different stages. You might have done this part first and then done the substitution for both pieces. Let's just do it here. Y prime is going to be negative 2k1 e to the negative 2t plus 3k2 e to the 3t. And into that, I can plug those other values. So let's leave that. Y prime is equal to negative 2k1 e to the negative 2t. Leave that empty. Plus 3k2 e to the 3t. And I'll leave that empty. Boy, I can't write much smaller. When for the initial conditions for the derivative, for the first derivative, when t is 0, 3, y prime equals 4. So now I have, again, e to the 0 is 1, so I have 4 equals negative 2k1 plus 3k2. So I also have this. Now I'm going to erase a little bit of what I wrote down here, just to erase the line around it. Because I'm going to put those two equations together. This gives me 4 equals, what did I come up with? Negative 2k1 plus 3k2. And that is a system of equations. And we did this in elementary algebra. So there are many different ways we could approach this. I'm not going to take the time to explain how to solve a system of equations. I think the approach that I would probably take here would be to multiply the first equation by 2 so that this variable gets eliminated. And then I might have to do the same thing here, or I could substitute. Either way, I'm just going to do this off screen. I'm going to end up with k1 equals and k2 equals 1 and 2 respectively. So now I have actual values for the k's in my solution. So I'm going to go down here and write my final solution, which is y equals k1, which I know to be k, e to the negative 2t, plus k2, which I now know to be 2, e to the 3t. And that is with two sets of initial conditions. That is how you go about finding the particular solution to a second order homogeneous linear differential equation. All right, there's a little bit more vocabulary we need to discuss here. This equation here is called the characteristic equation for the differential equation we have here. In fact, notice the coefficients here are 1, -1, and -6, and the coefficients here are 1, -1, and -6. And that is due to the very specific and intriguing, I think, nature of differentiating a function e to the rt. You take the first derivative and you get a single copy, if you will, a single power of r. You take the second derivative, you're going to get a second power of r, right? You're going to multiply this one by r again to get r squared. So this is called the characteristic equation. And when you solve this equation, you get two solutions. We know from polynomial, from our work in intermediate algebra, maybe elementary algebra, high school algebra 1 or 2, that quadratic equations have two solutions. The really nice quadratic equations like this one give us whole number solutions, or at least integer solutions, right? That's really nice, but it doesn't always happen. Sometimes you get quadratic equations that have two real solutions like this, but they're the same. And that's a particular situation we are not going to address yet. We will address it in a little while, in a couple of sections, but we're not going to address it here. That's one possibility. Another possibility is that these are not real numbers, right? If these are two non-real numbers, then that's a whole nother situation. And we're going to address that in another section as well. Well, that's going to do it for this one, but in the next video, we'll be talking about a more general case. In fact, instead of having just constants in front of my these two terms, what if I had functions, as I pointed out is possible in the first, I think it was the first slide of this video, where I outlined what a homogeneous differential, second order differential equation looks like. That's what we're going to be talking about next.